Temperature is defined as the measure of the average kinetic energy of the particles. What this means is that the faster the particles move, the higher the temperature, and the slower the particles move, the lower the temperature. It is not equal to the average kinetic energy, because if it was equal, then temperature would be measured in joules, but it's not. We call this idea of all particles are in motion, this constant state of motion, the kinetic theory of matter. Kinetic meaning moving, and so the matter is always in motion. And so it just kind of tells us about this relationship between the average kinetic energy and the temperature. Now, how do we change the temperature of an object? We do so by either adding or removing heat. So let's say that we have ice in water. The ice is not at 0 degrees, it's a little bit colder than that, and the water is above 0 degrees. And so what's going to happen is heat is going to flow from the hotter to the cold. Heat always flows from the hot temperature to the cold temperature. And so it will stop flowing once they are the same temperature. We say they're in thermal equilibrium. Now the temperature of the ice will increase because heat is added. The temperature of the water will decrease because heat is removed. And this brings us to our 0th law, our beginning law, which is the 0th law of thermodynamics. I don't know why they don't start with the first law. But they start with number 0. And the 0th law of thermodynamics is really just the transitive property. It says that if two objects are in thermal equilibrium with a third, then they're in thermal equilibrium with each other. In other words, if two objects have the same temperature as a third object, they also have the same temperature as each other. Now, temperature is a scalar, meaning it has no direction. It wouldn't make any sense to say that the temperature is 50 degrees Fahrenheit north. Direction doesn't matter in this case, but it still can be negative, even though it's a scalar. We really have 3 different types of temperature scales that we use today. The one that we use in the United States is the Fahrenheit. We're actually going to work backwards here, describing these temperature scales. The way that the temperature scale for Fahrenheit came about, it was developed by Fahrenheit himself. And what Fahrenheit did was he took his thermometer, and you need 2 points. On the first point, he put into a brine solution. That's a mixture of water, ice, and ammonium chloride, equal amounts of each. And he called that 0 because it was the coldest he could get at the time. Then what he did was he took body temperature and called that 96 degrees Fahrenheit. And we don't know for sure why he called it 96. Some people speculate it's because it's divisible by a lot of numbers. But he called it 96. But you say, wait a minute, I know that body temperature is not 96, not defined as 96, so what's the problem here? What happened was then, he found out that the boiling points of water and the freezing point of water were not nice round numbers. The freezing point was around 32, so he said, let's instead define the first point as the freezing point of water. Let's call that 32 degrees Fahrenheit. And the boiling point was around 212, so let's instead define the second point as 212 degrees Fahrenheit being the boiling point of water. This is going to adjust these two numbers, and 96 degrees gets adjusted to be now 98.6 degrees. Not a nice round number, but boiling and freezing of water is more important in the scheme of things than body temperature. So that's the Fahrenheit. The reason the Fahrenheit scale became prominent was because Fahrenheit was the first to use mercury as a thermometer. And so mercury was an excellent choice for a fluid because mercury will expand and contract over a large range of temperatures without freezing. And so you get very cold and it's still liquid, very hot and it's still liquid. So that was a benefit of his more so his thermometer, and so his scale gained prominence. Now what happened then with Celsius is Celsius wanted to make it more like the metric system, which is based off 10. So he called the freezing 0 degrees Celsius, but he didn't call the boiling 10, that would be too small of a scale. He called the boiling point then 100. And now what we need is we need a relationship between these two. How do we convert back and forth? What we see is we have 2 points that we can plot onto a graph. TF for Fahrenheit, TC for Celsius. The first point is the freezing point, which is 0.32. The second point is the boiling point, which is 100, 212. And so now we need an equation for that line, y equals mx plus b. M being the slope is rise over run. So how much did it rise? Well, it rose 180. And how much did it go over or run? It went over 100. And so this now reduces to 9/5. That's where we get that 9/5 value from. The y-intercept is simply right there, is 32, where it intercepts the y-axis. So we then get our equation. The temperature in Fahrenheit is 9/5, the temperature in Celsius plus 32. Now the Kelvin came about because we were trying to make everything positive. So if temperature is the measure of the average kinetic energy of the particles, that means as the particles slow down, the temperature gets less and less and less. This must mean that there is a lowest temperature. When the particles stop moving, that's the coldest you can get, because that's the slowest you can get. So through some equations and formulas between temperature and kinetic energy, we figure out that the coldest temperature we can get is at a temperature of negative 273 degrees Celsius. We are now going to define that in the Kelvin scale, so we don't write a subscript, as 0 Kelvin. And notice we also don't say degree Kelvin, we just say Kelvin. And so we're going to do a one-to-one relationship. For every Kelvin I increase a degree Celsius as well. So if I increase to 0 degrees Celsius, I increase to 273 Kelvin. And this gives us now our formula to get back and forth. All we have to do is add 273 to our Celsius temperature scale.